All right, let's continue with the discussion on well geomechanics, and welcome to the pre-recorded lecture of 11th September 2020. So we have been discussing well geomechanics. We had been introduced to the concept of three stresses: SV, S capital H, and S small h in the last lecture. Yeah. And we also talked about the pore pressure or the fluid pressure. We wrote it as PP. And we have drawn some preliminary pressure depth diagrams. Okay. So in the x-axis, we put pressure or stress. And in the y-axis, we had put depth. And we say, because this is with respect to EVD to vertical depth. So we said at the surface where the depth is 0, the pressure and the stresses are 0 as well. So it starts with 0, and then SV increases with depth. And how we calculate SV? By integrating rho EH, rho being, so rho 1, rho 2, rho 3, up to rho n being the densities of individual rock layers. Or we can approximate a gradient of 2.26. Sorry. Can approximate 2.26 bar 10 meter. Then we had S capital H. Yeah. And we said this is around 70% of SV, 70 to 80% of SV. And then we had S small h, which is the minimum horizontal stress, which is around 60 to 70% of SV. Right? Then we had introduced another term, which is pore pressure. Okay? And we said, in general, for hydrostatic gradient, the pore pressure is in the order of 1.15 bar per 10 meters. Okay? But this depends on the salinity of the brine, the function of salinity of brine. And for fresh water, it can be around 1 bar per 10 meter. And for saline water, it can be all the way up to 1.19 bars per. Okay, so this is the normal hydrostatic gradient. And we said that the pressure inserted by drilling mud must be, so let us say we call it as PM. Okay, PM must be more than pore pressure. Okay, and PM must be less than S small h. By the way, S small h is also called fracture gradient. Fracture gradient. We will see why S small h is called fracture gradient later on. Now, at a particular depth, whatever depth it is, you know, we can calculate the value of SV, S capital H, S small h, and pore pressure using this gradient. Yeah, so 2.26 bar per 10 meter multiplied by the depth, we can find out SV at any point, and then say around 80% of the SV we can calculate as capital H, and then we can also calculate a small h. And using this gradient, we can calculate pore pressure. So at any depth, I will have a, while we decide about the density of the drilling mud, so density of the drilling mud, rho of drilling mud will determine the pressure exerted by the drilling fluid. Okay? So PM is also a function of the rho of the drilling mud, right? So if we increase the density of the drilling mud, I will see I can put more pressure, okay, on the at a particular depth. And the pressure must, so the density must be designed in such a way that the at a particular depth, it's between the pore pressure and the fracture gradient. So we have a window of this to play with, and this is what we call as the drilling window. EW is the drilling window. We also said that if my PM is actually less than PP, then unwanted fluid will come inside the well from the formation. And if PM is more than SH mean or the fracture gradient, it will fracture the formation. Okay? So you can see with depth, my drilling window actually keeps on increasing, right? Which is a good thing. My drilling window keeps on increasing, which is a good thing. So I have more pressure to actually play with. But the thing can be very quickly get complicated, and we will discuss such complications right now. Okay. So to do that, let us again draw the pressure depth curve. Okay. So here is pressure depth, and let us say this is SV. Okay. And let's not be too bothered about S capital H at this moment. Let us just draw the S small h here, which is my fracture gradient. Okay. And then here is my hydrostatic pore pressure. Now, say for example, at a depth of say around 2000 meter, I encounter a shelly formation. I encounter shelly formation. Okay. That shelly formation will not do much to my SV and S small h, but that shelly formation can do something to the fluid pressure. What it can do to the fluid pressure, that it can shift the underlying rock's pore pressure by some bars. Nice. straight line. Okay. So you can see that before encountering the shell, it was following one particular gradient. Say this is 1.15 bar per 10 meter. Okay. And then after it encounters the shell, what happens? That the pore pressure makes a jump. Okay. And it's, although the gradient remains the same, but there is a overall increase in my pore pressure. Yeah, there is a step jump in my pore pressure. And this is what we call as overpressure. So what that overpressure has done, and you can see I have drawn above the shell and below the shell, and maybe within the shell, the pore pressure is, something like this. This can be a straight line, or this can be of different shapes. Okay, this can also be a straight line, no problem, or it can be a graph like this. It doesn't matter, but there is a step jump in my pore pressure, and that is what we call as overpressure. Now, if I have a overpressure, what I can see that my drilling window is reduced, right? So I have less pressure to play while I design my mud density, right? Now the thing become further complicated, and so far what we have discussed that the fluid here is water, right? Saturated, salt saturated water, which we call brine. So we have not discussed anything. So we have not discussed anything about hydrocarbon as yet. Everything, so whatever subsurface situation we are looking at, the pore pressure, the pore spaces is filled with water molecules, right? Not, there is no hydrocarbon. That's what we have drawn. Now, the thing can get even more complicated, and we can draw the pressure depth curve again. Okay. Let us just draw the S small h. Here is my S small h, or my fracture gradient. And then I have drawn my pore pressure, okay, which is at the top, which is at the top like this. Then perhaps it sees a overpressure. So there is a shift, and then continues with a different gradient. So follows the same gradient. Follows the same gradient. I think I should not properly drawn parallel to this line. Okay. But there is a overpressure shift. There is a virtual shift. So my drilling window is reduced. Now, for example, so this has happened, say, at depth of 2000 meters. And then, for example, I have a sandstone layer. Okay? I have a sandstone layer. Maybe after that, I have sandstone layer. And at that sandstone layer, up to 2000 to 2050 meter, okay, I have hydrocarbon. Okay? And say, for example, this is gas. So what will happen? Hydrocarbon will have a different fluid density, and the fluid density will be perhaps like this. So you can see my pore pressure now, at this space, the drilling window is further reduced. Okay, because the gas will have a gradient of around uh, 0.2, 0.2 bar per 10 meter. So this is further reduced. So this point we have already discussed is called GWC, or gas water contact. So my drilling window is further reduced. Okay. So, and in this particular case, I have, maybe if the gas column stops somewhere here, I'm fine. Okay. If the gas column stops somewhere here, I'm fine. But if the gas column virtually continues all the way up to the fracture gradient, what I will observe that there will be, you know, hydrofracturing, hydrofracturing of the rock. So my topsill might breach. This can lead to my topsill breach. Okay. So if my fluid pressure is so high inherently that it is actually crossing the fracture gradient. It is crossing the fracture gradient. Yeah. Here I can imagine that the topsill must have leaked. Okay, but if it is not the case, I will still have a drilling window, but the drilling window is reduced, is very, very reduced. So in this particular case, I have to actually play with a very small, I have to be very precise while I design my mud density to drill this particular section. Okay, because for the presence of this gas, this is further reduced. Okay, now if it is in case of gas, if it is oil, then I will use the gradient of oil, which will be, of course, a function of the density of the oil. Now, one of the things, one of the easy numericals that you can calculate, maybe I can ask you to actually calculate the value of the drilling window at a particular depth. Okay? So maybe if I ask you to calculate what is the value of the drilling window, so that means I have this fracture gradient, this pressure, and then I have to calculate that. I have to calculate the pore pressure at this point, and the difference between fracture gradient minus pore pressure will provide me my drilling window, right? Now, how to calculate that? So first thing that we have to do, we have to draw the, we have to calculate the pressure at GWC. So pressure at GWC is equals to, you know, so I have to go up to, say, up to this depth where my overpressure starts. Say this is D1. Okay, so D1 multiplied by 1.15 bar per 10 meter. That will provide me the pressure here. Okay. So this is this pressure. Say let us call it as P1. Okay, plus the, okay. Now I can actually calculate the pressure all the way up to this point, right? Yeah, following the gradient. So let us say this is, rather than that, this is my D1. This is D1. I don't know. This has, let's do that exercise in a clearer canvas so that I can explain it better. Okay. So I have to calculate, if I have to calculate the drilling window with all these complications. So here is my SV, that is 2.26 bar per 10 meter. So, for example, I have been asked to calculate uh, the drilling window at a depth of D1. Okay. So what I have to do, and then maybe I have been given a depth of DWC, which is D2. Okay. So if we draw that, so here is my normal hydrostatic gradient. Yeah. And here is my fracture gradient. So, so the depth GWC is, and say I have been given an overpressure which is OP, whatever the value it is. Okay. So suppose the overpressure starts at this depth. This is where my overpressure starts. So from here, I will add the OP, and that will provide me a gradient like this. Okay, so this is my overpressure. Okay. Now, say I have said my FWL is at a depth of E2. Okay, or GWC is often called FWL or free water level. Okay. For the timing, remember they are the same thing. Okay. So here is my D2. So first thing that I have to do, I have to calculate S small h at D2. How would I do that? S small h at D2 will be D2 into gradient. So first I have to calculate SV. SV will be 2.26 bar per 10 meter multiplied by D2. That will give me SV at this point. Okay. So S small h will be SV multiplied by say 80%, okay, or 70%, whatever it is given. Say this is 70%. Okay. So I got S small h as at D2, which is this value. Then I have to calculate uh, the pore pressure at D2. So pore pressure at D2 is equal to at D2 is equals to D2 multiplied by 1.15 bar per 10 meter plus the overpressure. Okay, so that is the pore pressure due to the water at the gas water contact. And then what I will do, I have to calculate the pore pressure at D1. So pore pressure at D1 is equals to pore pressure at D2 minus 0.2 per 10 meter multiplied by D2 minus D1, because the pressure is kind of, so here the pressure will be less than this one, but the decrease is happening with gas gradient, right? So that I have to do. So I have got pore pressure at D2 minus pore pressure at D1, this value. Then similarly, like I have calculated the SV at D1, I can also calculate it. I can also calculate S small h at D1. Okay. So my drilling window will be S small h at D1 minus pore pressure at D1. Okay. If we do that, I will be able to calculate my drilling window, which is nothing but this value. Okay. Now, larger the drilling window, it is more easier to drill that particular well in that section. Okay. So the philosophy is simple. You have to calculate a small h at the depth where you want to calculate the drilling window. Then you have to calculate the pore pressure. So the pore pressure will have three components. One is the hydrostatic gradient. Then I have to add the pore pressure. Yeah. And by that you will come to the you have to calculate it at FWL or at GWC. Then you have to go up at that particular depth where you want to calculate your pore pressure, and that will be minus the pressure due to the gas gradient, and you can calculate your uh, drilling window, right? Now, how to how in life this how in life this fracture gradient is calculated, because calculation of fracture gradient is absolutely an important thing. Okay? And this is done by something called leak-off test. Okay? And we will show you what leak-off test is all about. Now you can see here what is being shown here is essentially the configuration of few wells, configuration of a well at different condition. Okay? So what you can see here is the bottom hole. You can identify now this is my casing. This is my casing. And through this, so to this, I will have the inward flow of the drilling mud. And then through this, I will have my, for example, I will have my outward flow of my drilling mud. Okay. So, okay, through this pump, the drilling mud is being pushed inside. Okay. So it's essentially is pushed inside through this. Okay. To the drill pipe itself, as you have seen in the video, if you remember. Okay, this, because this is hollow, and then it actually circulates back, and it can fill it up. Now, in normal, so this is without any drilling mud. This is what we call well static when there is no drilling mud. And the normal circulation means I am whatever my input of the drilling mud is exactly equal to the output. So whatever is being pushed inside, yeah, is coming out of here. And this happens while we actually uh, this happens while we actually drill the well. Then there is called circulation with a rotating head. What we do here, we actually stop the input, but we keep the output. Okay? And then there is something called kick circulation. You know, or during leak off test, what you essentially do during leak off test, you close this output, okay, and you keep on increasing the drilling mud through it. So what I am doing essentially, I am increasing the pressure of the bottom hole. Okay, I am slowly keeping on increasing the pressure of the bottom hole. Okay, so the pressure of this section is keeping on increasing because I have stopped this valve, but I am still keeping on pushing the fluid, right? So what will happen? I will kind of think of a balloon and I am kind of keeping on pumping that balloon. Okay? And there will be a particular time when this balloon will burst and there will be fractures created in the formation. And the fluid that you are using to circulate will, get into the formation. Okay. So this is all about the test, and this essentially when this particular rock will break and the fractures will be created depends on the elastic modulus of the rock. Elastic modulus of the rock. If the elastic modulus is less, then of course, I mean, for example, Young's modulus is less, it is easier to fracture this formation. If the Young's modulus is higher, then it will be difficult to fracture this formation. Okay. So now if I look at the next picture, it will be further clearer. Okay. So what you can see here in the x-axis, I have plotted volume pumped. I mean, because I have stopped that outflow, it's only the inflow that is happening. So I'm keeping on increasing the drilling mud, and hence the pressure in the hole is keeping on increasing. Okay, so the pressure is keeping on increasing. Okay, and till the elastic limit of the formation, the pressure will keep on increasing. And then after a point which we call as the leak off point, there will be smaller cracks or micro cracks will generate. Okay? So I can see that there will be some mud which will be lost. So there will be a reduction in pressure. If I keep on measuring the bottom hole pressure, I will see a reduction in pressure because through those smaller micro cracks, yeah, some of the fluid will flow into the formation. And this is what we call as leak off point. Okay. And then there will be a point, but still the pressure will increase. But there will be a point which is called ABP or fracture breakdown pressure. At that point, larger crack will form. Okay. And a lot of mud, this drilling mud, will be lost in the formation. And this is what we call as mud loss. This is what we call as mud loss. So at a particular point, there will be macro failure. So this is the point of macro failure. Okay. So this is the point of micro failure. This is the point of macro failure. At fracture breakdown pressure, and a lot of mud will be lost in the formation, and the pressure will be, there will be a sudden jump in the bottom hole pressure. Okay, the BHP or the bottom hole pressure, the pressure that you measure at the wellhead, okay, that will be lost. And then with the volume pumped, your uh, bottom hole pressure will be kind of coming at an equilibrium. Okay, so there will be a period where there will be some undulation in the pressure. That is what we call as fracture propagation pressure. Fracture propagation pressure means this is the time when the fractures actually grow in length. And then instantaneous shut-in pressure where the, uh, the pressure kind of comes to an equilibrium. Okay? And this is what we call as leak-off test. So this particular point, kind of provides me as the SH min, or minimum horizontal stress, or the fracture gradient. Okay? So if I do that test, say at D1, and I measure this LOP at D2, I again measure the LOP at D3, I measure my LOPs, okay? And then I plot, LOP1, LOP2, and LOP3, and if I join them, okay, so this is LOP pressure and here is depth, I will be able to construct my fracture gradient or my minimum horizontal stress. Okay. So if I go back to the whiteboard, I go back to my whiteboard. So with leak-off test, I can calculate S small h, or what we call as fracture gradient, which is an absolutely important uh, parameter in determining the well stability. Okay. Now, and the pore pressure is generally calculated by pressure gauges, and these values are called RFT values. Sorry, these pore pressure values are called RFT values, or repeat formation test values. Okay, so by measuring the fluid pressure, which we call as RFT measurements, we calculate pore pressure, and by doing the leak-off test, we calculate fracture gradient. Okay, and then we essentially construct my fracture gradient curve, and then also we construct our pore pressure curve, right, which can look something like this. This is the gas gradient, and hence we can calculate drilling window. Okay. Now, there are two more things that I want to discuss today. One we call as EITF, and that stands for drilling induced tensile fracture, and another one we call as breakout or we also call it as borehole breakout. Okay. Now, while drilling, I mean, leak-off test is a controlled thing, right? You are by yourself actually increasing the mud pressure so much that it crosses the fracture gradient and it creates fracture in the formation. Okay. Now, the drilling-induced tensile fracture and borehole breakout, they form while you are operating regularly. Okay, but you, by mistake, maybe you have actually enhanced the drilling-induced. Enhanced the uh, MP or PM, the fluid pressure of the drilling mud. Okay, so what happens? That suppose I am looking at a borehole. Okay, and this is the cross section of a borehole. If by mistake the mud pressure becomes more than the uh, fracture gradient, or becomes more than the minimum horizontal stress, okay, we create two types of fractures. Okay, one are shear fractures. Shear fractures are generally occur as conjugate fractures. Okay, so two sets of fractures. What are shear fractures? We will study in our structural geology class later on in the next semester. But for the time being, remember they happen as conjugate pairs. Okay, and they are generally, this acute bisector of the shear fracture is parallel to S capital H. Okay, so there are fractures at one direction of the borehole happens. So due to this fracturing, the circular borehole takes the shape of an eye. Takes the shape of an eye. Because of this fracturing, some material gets, eroded from here, and falls behind. So this eye-shaped borehole that forms due to the shear fracturing is called borehole breakout. Okay, and if I find this from these borehole breakouts, they actually provide us very important information. What information do they give? That if the borehole breakout is, the axis of the borehole breakout is like this, then the S capital H is actually perpendicular to the borehole breakout axis. So S capital H, maximum horizontal stress, is perpendicular to the borehole breakout axis. On the other hand, there is another type of fracture happens, but sorry, this has become a ellipse, but we will draw a circle. There is another type of fractures that generates. Okay, this is pretty much a circle. Let's just draw cylinder actually to represent the borehole. Not of my best drawing. Let me just draw it properly. Okay, this is the circular top part of the cross section of the borehole, and this is the borehole in 3 dimension, if you like. Okay, suppose this is the direction of S capital H, and the S small h will be perpendicular to it. So there will be another type of fractures generated, which will be, parallel to the S capital H. There will be fractures generated which are parallel to S capital H. And they are by nature are tensile fractures. They are not shear fractures, they are tensile fractures. What is tensile fracture? What is shear fracture? We will study them in detail. But tensile fracture, for the timing, remember they are like a single fracture, okay, and happen parallel to the S capital H. Okay? So from if we can find out this as tensile fractures, and now if I draw this, okay, here is my borehole, the circular shape of the borehole, and then I have got my tensile fractures. Okay. So my S capital which H will be parallel to the DITFs. Okay. So these tensile fractures are called drilling induced tensile fractures. This also happens when my mud pressure is more than the fracture gradient, but these fractures are tensile fractures, but they are parallel to the S capital H. So if I find a if I now want to find a borehole breakout here, the borehole breakout will be oriented perpendicular to the drilling induced tensile fracture. Okay, so maybe at one depth I find a borehole breakout, and in another depth I find drilling induced tensile fracture. That will help me to characterize and cross check if the direction of S capital H is important or not. I mean, is matching or not, because they will form perpendicular to each other. Okay. Now, the for the timing, I don't want to get into further details, but remember, finding out the direction of S capital H. So finding the direction, finding the direction of S capital H is very important, especially with respect to drilling horizontal well. Okay, and remember that while you drill a horizontal well, it's actually advisable in terms of wellbore stability, where your wellbore will be most stable, if I can drill my horizontal well parallel to S capital H. Okay, if I can drill my horizontal well parallel to S capital H, yeah, my wellbore will be most stable. Why? I'm not discussing it right now. Maybe you can read about it, but I don't think we have enough background to understand that at this particular moment. Maybe we can come back to this later on. For the timing, remember, uh, a horizontal well's leg is maximum stable if I drill the well path or the well trajectory is oriented along S capital H. And how do I find S capital H? I find them by studying borehole breakouts and drilling induced tensile fractures. And where do I study drilling induced tensile fractures and borehole breakouts? Are in image logs. Image. Okay. So these are some geophysical logging technique by which you can take pictures of literally the pictures of the borehole, and you can determine where the DITF, where the DITF or the borehole breakouts are present. Okay, that you find this particular information you can find from image logs. So the image logs will provide you the orientation of the drilling induced tensile fractures, and borehole breakout. So while we study petrophysics, while we study logs, you will find out, you will see image logs, and I will show you how these drilling induced tensile fractures and borehole breakouts look in an image log. Okay, so I'll stop the lecture here, and I will see you next week. Thank you.